Hey guys, hi, this is Radhakrishna. Welcome to my channel. In this video, we're going to talk about Indian remote sensing satellite data and how does that look, what that scene contains when we order from Bhoonidhi, right? So in the last video, I showed you all how to browse data using different features of Bhoonidhi, how to download a free data set if the data sets are free, and how to order the data set if that particular specification of the satellite sensor combination is a paid dataset. So I have ordered a dataset which is like an ISRO satellite. So I will be showing you all a scene from Resourcesat 2A. So this is like it will be interesting if it is the first time that you are looking at the ISRO satellite data. I'll be showing you all what is the satellite actually capture, right? So all of that I will be showing, and also I will be showing you all how to begin analyzing the satellite data or the scene that you've ordered, right? So how to understand some parameters that are inside the satellite data, so on and so forth. So before going into all of that, just to mention that all of that I will be saying in this particular video is my personal stuff, that there is nothing that is official. And one more thing is, whatever I'll be showing you all is just a small segment of things that satellites do. So there are missions, different missions that are satellites are tasked to do. Like there are communication satellites, there are weather climate satellites, there are satellites or orbiters that go around other bodies other than Earth, like orbiters around Moon and Mars and so on and so forth. So I'll be showing you all Earth observation satellite data. How does it look? What are the different parameters that are usually considered while analyzing the satellite data, so on and so forth, right? So whenever you order a data set from Bhoonidhi, right, you will be getting a mail that okay, your scene is ready in an FTP server, and when you download it, you will be having this before you. So this is a folder, and inside this folder you will be let's just go into that. So you will be having these things, right? So there are 4 bands inside this folder. This particular satellite is Resourcesat 2A and the sensor is list 3. So when we open this list 3 of data set, or let's say we see what is inside this meta, right? So there are around 120 attributes inside a meta file, and we'll go through all of those parameters initially. So product ID and OTS product ID are like unique identifiers for ISRO's processing. We've got SAT ID sensor. SAT ID is like the satellite that we are, the satellite that has captured this particular scene, which is IRS R2A, which is Indian Remote Sensing Satellite Resourcesat 2A, and the sensor is list 3. So if you want to learn more details about this satellite sensor combination, you can just Google it. There's a very big and good detailed handbook that is available. In the handbook there are a lot of details on what is the satellite, what is this payload all about, what are different spectrum that this payload is observing, and so on and so forth, right? And all the different attributes after this only we will be able to really comprehend when we go through that particular handbook. I will also show you a glimpse of that handbook so that we are able to realize what is inside this meta file. So let me just open the handbook initially before showing you all. Okay, I have opened that. Let me also link that initially so that you are able to see. Okay, so what you're able to see is the handbook. Resourcesat 2 I have opened. You will also get one for Resourcesat 2A. So in this index you can see that there is all different details starting from mission overview, system overview, how ground segment gets the data, what is the payload actually made of, what are different modes of acquisition, how the planning is done, how the different reference scheming is done, right? And there are different details that you can go through. Data reception systems, how do we acquire the data, what are the different pre-processings that we have to do for the packets to get an actual raw data, so on and so forth. So this is a publicly available handbook, different procedures for calibration of the data, how do you order the data, so on and so forth, right? So let's quickly circle back to the metadata. So we've got like sensor, we know. Then we have path row. What is path row here? Path row is nothing but a scheme that was designed to efficiently identify a particular area with respect to Resourcesat 2 satellite or Resourcesat 2 different scheming, right? So here path means that, okay, so you just imagine Earth, right? And Earth is divided into equal number of grids, okay? And each of this grid is identified with a number, and in the x-axis, right, you identify it with a path, and in the y-axis you do it with a row, okay? So when you go to path number 90, right, in the x-axis, and row number 50, this particular scene, whatever we have downloaded, corresponds to that grid of reference scheme. So that is what is mentioned here. But if you want to really get to the details of what is the path and row that is mentioned, details are available in the handbook, as I have already told you. So different things are available here in the handbook. You can go through that. I will sort of try to look at it. If it so you are able to see what are the different starting points and ending points for rows here, latitude, longitude, and for paths also, latitude and longitude. So using this, if you construct a shapefile or a grid, you will be getting grids, and over that path and row you can easily identify. This is done because these satellites are sort of very systematically planned satellites. So if you are aiming for a path and row today, after a certain time period it will image that path and row again. So that is called temporal resolution, as in after that specific amount of time the satellite will go on to that path row again to image it, right? So this is systematic observation, and that is why referencing scheme is actually made, because the systematic planning is done for observing the Earth. So following that, we've got date of pass. Date of pass means whenever this scene was captured by satellite, what is the date on ground. We've got number of bands. So in this satellite there are 4 bands. Band numbers are given 2, 3, 4, 5. What are the different bands, right? If you want to also understand that, you can just search for RS2A bands, right? Easily searchable. You will get all different details of what is a band, right? So here it is given band 2 is between 0.5 to 0.59, and band 3, band 4, and band 5, right? So these are, why don't we start it from 2? Because it's just a nomenclature that they've adapted in those times. Band 2, band 3, band 4, and band 5. Band 5 is actually sphere band, shortwave infrared. We've got 4 is near infrared, 3 is green, and 2 is red, I think. Yep. 2 is green, 3 is red, 4 is near infrared. We've got pass type. Pass type is specified for a ground station. This does not actually impact users. We've got date of dump. Date of dump means when the satellite has actually dumped this data on the ground station antenna. So that is also 17th April. So it's like we have imaged on 17th April, we dumped on the same day. So when it is dumped on the same day, the probability of getting the data on the same day is also quite high, right? So today you have imaged, today you have dumped, and after a small processing time, this data is cataloged and available on Bhoonidhi. So you can order the data then and there. We've got dumping orbit and imaging orbit, and orbits, right? Orbit number. When we talk about orbit number, it is also something special. Orbit number. Orbit number is like whenever a satellite is launched, right? Earth observation satellite specifically. These satellites, right? When Earth is rotating, the satellites go from pole to pole, pole to pole. All of this times they do orbiting of the Earth. So for each orbit, we give it an orbit number, first orbit, second orbit, third orbit, from the time it has launched. So this is a standard that is followed, and this number is also given in two-line elements. If you don't know what two-line elements are, I have a detailed video about that. Two-line elements. Two-line elements, just to give you a one-line introduction, they are two-line phrases, like a set of numbers that actually give you understanding or rough approximation of where that satellite was at a particular time, right? You can actually propagate it forward as well. It will be true close to that particular time when the two-line element was generated, right? And this TLEs, right, two-line elements are published for all different satellites. So one of the element of two-line elements is also orbit number. So that is the same orbit number that you're seeing here. Dumping orbit and imaging orbit means that in the 22,621th orbit, it has imaged and it has dumped in the same orbit. It has not gone even into the next orbit. So it has imaged, it has dumped, and then it has gone into the next orbit. So that means that particular information means that. And you've got bytes per pixel is 2 and bits per pixel is 10. So what this means is that each pixel of this particular image is having 2 bytes of data, but the actual image content is restricted to first 10 bits, right? So the bits that are falling after the 10 bits, right, you've got like 6 more bits inside it because it's 2 bytes. So all those 6 bits are not really useful, right? So that is one thing. Generation date time is like at 12:27. Okay. Product code. So product code is also a standard at NRSC. So this is a set of some letters. Each of this pair of letters or letter specify a certain meaning. So first 2 letters meaning standard, U meaning UTM, right, and C meaning cubic convolution resampling, and GTD meaning georeference, TIFF, etc., etc. So that is product code. So how this is product code is generated basically from the options that you put on Bhoonidhi, right? While you're ordering, you choose some options, what you want. You want a standard product, what is the projection you want, what is the resampling method that you want the NRSC to use when we are resampling it into a certain grid level, and how do you which level of correction that you want, georeference, product, or the product, or rad product, so on and so forth. So the product type is mentioned, georeference, G means that. Next we've got input resolution and output resolution. So these are specific. Input resolution is actually specific to data processing algorithms that I think ISRO uses. So it takes 23.5. Output resolution is like the resolution of the TIFF, geotiff that is given inside the particular scene. I will also show you once I open this data. I will also show you that this is like in meters, 24 meters. So each pixel is, they are saying that each pixel, it gives you 24 meter of ground value. So the next things are the same things that we've seen in the product code. Then number of scans in pixels, meaning the number of rows and columns in the image. We've got start pixel is 0, map projection is UTM, datum is WJS84, ellipsoid is the same. You've got product and image, upper lat, lawn, etc., etc. So all of this we will clearly understand when we open an image. So let me open the image for you. Let me open the image. So as you have seen, right, so there are 4 bands inside the scene that we've got. Inside the meta also we have seen that there are band 2, 3, 4, 5, right? So I'll show you how does that look. Okay, so we are opening QGIS software to visualize the satellite data. So this is the software that I use to work with satellite data. So let me build a miscellaneous satellite data first. So this is the data that I was browsing. So I take all of the 4 bands and I construct one TIFF. So we will get that soon. right. Okay, so we've got the satellite image over here. Now what I want to do is I want to visualize it. So this is called as a false color composite. So this is the satellite data that we ordered. Friends, this is how the satellite data looks. So what I have done, I will explain to you. So I have made a single TIFF out of the 4 TIFFs that were available. I will also open those 4 TIFFs individually so that we get a good understanding of what is actually happening in the background, right? So these are different four TIFFs. Let me group them first, right? So these are all those 4 TIFFs. What I did is I combined all of them into a single image so that we see a color image, right? So this is a color image that I'm playing with, and this image actually has 4 bands inside it, but we can see only the combination of 3 bands, right? Because our display is made of 3 color combinations. So we've red band, we have green band, and we have blue band. So this is 3 to 1 combination. When I say 3, it is actually a 4 because my 2, 3, 4, 5 are matching to band 1, 2, 3 and 4 here. So this 3 is nothing but near infrared, red and green. So what image that you're seeing here is called as a false color composite, right? And in this, most of the time red indicates that there is some sort of vegetation component that is involved with that particular pixel. Now let's get back to the metadata and try to make sense of what we are seeing, right? So we are having product and image corner coordinates, right? So what is that all about? What is product coordinates and what is image coordinates? So see friends, we are having an image here and the image is slanted. Can you think why this is the case? See, when a satellite is going from pole to pole, the satellite is going in this way, right? And in the same time the earth is also rotating. So when the satellite is going from pole to pole, the earth is rotating. So when it is going to image the further lines, it will actually image a portion which is on the left side or right side depending on the rotation direction, right? So the image will be slanted, right? And that is why we actually have the actual data pixels in a slanted way. Now any image format will be rectangular, right? And so what processing does of this satellite image, right? We take the data pixels, although in the raw format we get them in a particular rectangle way only, but after due corrections that we do from different sensors data that are available on board, we understand that the first line data is not exactly beneath the second line data, but the first line data is actually ahead of the second line data, and so on and so forth. So this is the step way that is actually constructed, and the adjacent, the left and the right bottom, we have a little void, right? So there we fill no data pixels. This is the same case with any sort of earth observation satellite that you do earth rotation correction, you get this void pixels. So this is called no data. Okay, so we fill it with zeros, so this is called no data. And here the product and image coordinate, corner coordinates refer to this difference itself. So when we talk about image, right, so product, right, so this is the product and image is this. So the corner coordinates will be given for these pixels in image and product will be given in this corner coordinates, so the whole image with 0 pixels combined as well. So we have seen that bit of metadata. Again, let's go to the metadata. We have map coordinates now. Map coordinates are nothing but projection coordinates. So there are different types of projections, friends. What you're seeing is a UTM projection. These are in the bottom you can see coordinate and it is displayed in some huge numbers. These are nothing but a different form of representing latitude and longitude. Depends on what is something that is good in representation. So Earth is a 3D object, right? but you want to see it on a 2D screen or a 2D map, what you do is you sort of have a function that maps 3D space to 2D space, and there are different sorts of functions which have different attributes to them. Some functions are good in conforming, in actually maintaining the area that is represented. Some functions are good in maintaining distances. Some functions are good in maintaining features, right? So depending on those functions, we basically call them as projections. So this is a UTM projection. You can read a lot more about these projections online, right? So this is a UTM projection, and what you are able to see here in this particular metadata is prod map. When you see map coordinates, they are in the particular coordinate system that is that the scene is in, basically. So all of that we talked about it here, right? Projection is UTM. Now then we've got scene center, latitude, longitude. So all of these functions, right, they are interconvertible. So you can take a coordinate in one projection, you can convert it into the coordinate of another projection if at all they are convertible. So latitude, longitude is anyways available all across Earth, right? So you can convert UTM coordinates into latitude, longitude, and the scene center, latitude, longitude are calculated thus, that are displayed here. You've got false easting, false northing, zone number. All of these are parameters that are inputs or describe the function, the projection function of UTM. We've got scene center time. This is also something that is interesting. So this is a acquisition time. So whenever it is imaging this scene, right? So whatever the satellite data I have shown you right now, when the satellite is over that particular area, what is the time, right? This is universal time. So that is the scene center time. You've got scene center roll, pitch, and yaw. So these are satellite attitudes, how the satellite is oriented, right? These are roll, pitch, and yaw. And we've got satellite azimuth at center and elevation at center, the satellite where the satellite is actually located at. We've got heading angle, we've got incidence angle, we've got satellite altitude. All of this altitude will be in kilometers, angles in degrees, I hope, and then tilt angle, there's no tilt, right? And then we've got Dem correction is yes. Basically what Dem correction indicates is like whenever they are processing this particular satellite data, right? Again, let me just go back to the satellite data so we have a good understanding of what I'm talking about. So whenever we are processing this data, how this data is processed, right? So there is an ellipsoid of Earth, then the satellite is looking at a particular point on this ellipsoid. Let's say this is the ellipsoid, and satellite is looking at a particular point on ellipsoid. This ellipsoid is not flat, right? So Earth is not flat, there are different mountains on Earth. So if I'm looking at a particular mountain, it obstructs the view that is left side of it. So when we actually take the digital elevation model and we do the processing, right? So some of the pixels are obstructed, some of the pixels lie at a particular latitude, longitude on a 2D representation. So all of the terrain effects, those are corrected in what you say Dem correction. That's what you were seeing in the metadata. So it is saying that that correction is applied, Dem correction is applied. And source of attitude and orbit are like the parameters to the processing, what is the source of orbit and attitude that is available on board, so on and so forth. So there are multiple sources of orbit and attitude. That is why they are giving this things, and this is a public data set. So this is a public metadata that anyone can get. There are temperatures Lmin and Lmax. These are saturation radiances and zero radiances. What is the maximum radiance that you can get in band 2, band 3, band 4, band 5, and there are standard units that is available in the user handbook. You can get it. Quality is sparse, cloud percentage is not available. You've got a cross track accuracy, a long track accuracy, satellite heading angle, again scene start time, scene end time. So we've got like scene center time we have seen, but this is the scene start time. So the acquisition started at 30 seconds, 5:58:30, and then the scene end time is like 5:58:52. So the scene was acquired in the range of 22 seconds, right? And in that 22 seconds itself, you could see that there was that much rotation of Earth visible at that particular altitude of 822 kilometers. Yes, obviously there will be. Again, we've got like incidence angle, along track, across track. All of these are components that are divided into the image, and because that is why you sort of see along track and across track parameters, right? Because there are certain errors that you could correct with this division of components. View angle and product start, scene start time and scene end time, the same things, right? So this is metadata. Now let's get into the actual product and talk about what we are seeing here. So we are seeing a combination of three bands, near infrared, red and green. Here red indicates, as I said, it's indicating that there's a slight vegetation component to it. You can see water, you can see cultivation and a lot more, like the desert lands here, right, so on and so forth. So let's see what SWIR band gives. So this is a combination of SWIR, red and green. So you can play with it. This is just for visualization, right? But if you actually want to see what this data is actually made of, these are the values that you can look at. So at that particular pixel, band 1 was 166, band 2 was 160, band 3 was 203, and band 4 was 252. What do these mean? These are DN values, okay? You can convert these DN values into physical parameters at satellite, that is the radiance that is observed at the satellite, using some biases and multiplication factors that are available in the metadata, right? So using that you can convert it into radians, but if not, also you can, if you want to use them directly, you can use them. And there are many ways of using this, right? If you want to correct them, and if you want to measure two different scenes, you would obviously do that in radiances. You convert these DN values into radians. And if you sort of want to apply some machine learning algorithms, right, you want your model to be really generic. You don't want to really depend on radians conversion formulas and all. You want your model to work irrespective of how the image is looking in the form of radians. So you work on DNs itself, because your models, deep learning models and all, work on how the image actually looks like. So you acquire a lot of images with respect to all different seasons, all different climate conditions, all different haze, cloud, etc., etc. You put them all into training data sets and you make your model really generic. So that is one way of looking at it. There's also some more things that can go into data analysis, like there are indices or combinations of these bands. There are arithmetic combinations, I could say, like NAVI for example, right? It is like NIR, the value of NIR, which is near infrared, minus the red band by NIR plus R. When you do a normalized differential of these two bands, NIR band and R band, you sort of get a indication of how the vegetation is, right? This has been used very extensively in vegetation domain, agriculture, non-agriculture, everywhere. And there are indices that could indicate if that pixel is water, if that pixel is urban land, if that pixel is actually polluted, so on and so forth. There's multiple indices that are there, and all of these indices, right, they are nothing but statistical indices, some combination that is indicating something on the ground. So this is how analysis is done, statistical or even AI ML models, or if you want to do physically point this pixel representing this, how it looks like. So yeah, this is RS2A data. If you want to do analysis on it, Bhoonidhi is open. Thank you.